Our work with solving equations began with using just addition and subtraction, and now we're going to transition to solving equations using multiplication and division. Remember that everything we do is going to have to be balanced, meaning we need to follow that golden rule of algebra. What we do on one side of the equation has to be identical to what we do on the other side. So if we multiply one side of the equation by a number, we have to multiply the other side of the equation by that same number. And it should be a non-zero number or things get really simple and don't really help us. Also remember that when we solve equations, we're going to be writing equivalent equations. Meaning, if we have x over 2 equals 3, we're going to work to isolate x to get x equals 6. These two equations are said to be equivalent. And we got from one to the other this way by multiplying by 2. And then we could also have 4x equals 12, which, if we did our work, would mean x equals 3. We would get that by dividing by 3. These are equivalent expressions. This is equivalent to this, and this is equivalent to this. We are isolating the variable, creating equivalent expressions. Here's an example problem. We could have negative 5x equals 7. In order to isolate 5, we need to get rid of that negative 5, and negative 5 is being multiplied by x, so we know that the inverse operation to multiplication is division. So we are going to divide both sides by negative 5, which means that the negative 5 here is going to cancel with the negative 5 here, leaving us with x is equal to 7 over negative 5, which you could also write as negative 7 over 5. Either one is fine, but we've undone multiplication with division. We divided both sides by the same thing. What about if we have division to start with? For example, we could have x over 5 equals negative 30. In this case, x is being divided by 5, so we need to multiply by 5. In this case, 5 over 1 is 5 on both sides. We're doing the same thing to both sides, so we're okay and still abiding by the golden rule of algebra. In this case, the 5 here and the 5 here, they cancel each other out, leaving us with x is equal to negative 30 times 5, so x is equal to negative 150. We could check this, if we wanted to, by taking 150 and putting it into the original expression, which was x over 5 is equal to negative 30. We could take our negative 150 and plug it in right there. And what we get is negative 150 over 5, which does indeed equal negative 30, so it does check, and we are happy. What you end up with are these rules, these properties of equality. You have an addition, subtraction, multiplication, and division property. If a equals b, then a plus c equals b plus c. Holds true right here. And then you can do the same thing with subtracting c. And here we're multiplying both sides by c, and here we're dividing both sides by c. So all four of these things are true, and they hold equality. You get equivalent expressions if you perform these operations. Here's a word problem. The usual rate for taking and projecting professional movies is 24 frames per second. Find the total number of frames in a movie that is 90 minutes long. First, we need to set up a verbal model. Here it is. The total number of frames in the movie divided by the total number of seconds in the movie is equal to the number of frames per second. We know that the number of frames per second that's given to us is 24. So we know this is going to be the number of frames per second. We're trying to find the total number of frames in the movie, so we can call that x. X is going to be that total number of frames in the movie. What we do need to find, though, is the total number of seconds in the movie. And that can be figured out by multiplying 90 minutes times 60, because 60 seconds are in each minute. And that's going to be 5,400 seconds. This leaves us with the expression x over 5,400 equals 24. We now need to solve this expression for x. We're going to do that by undoing the division that you see. Dividing by 5,400, we need to isolate x, so we are going to multiply by 5,400 on both sides. 5,400 on the other side, remember it's over 1 just to be clear. And now we know that the 5,400 on this side cancels here, leaving us with the expression x equals 24 times 5,400, which equals, and I had to break out the calculator for this, equals 129,600. So that's how many frames there are in the entire movie, right here. So now let's move on to section B. If a worker can restore 8 frames per hour, how many hours of work are needed to restore all of the frames in the 90-minute movie? First, we need a verbal model, which is going to be the number of frames restored per hour times the number of hours of work is the total number of frames in the movie. Well, we know from our part A that the total number of frames in the movie is 129,600. And we know that the number of frames restored per hour is 8. Now we can label the number of hours of work y, and now we need to solve this expression. 8 is being multiplied by y, which needs to be undone by dividing both sides by 8. So we end up with y equals 129,600 over 8. And that's equal to 16,200. So that tells us the number of hours needed to restore this movie. That's a long, long time. To put that in perspective, that would be a total of, let's divide it by 24 to get days, 675 days of work. 675 days of work. That's a long, long time. That's a little under 2 years. Long time. So we hope you'd have more than one person working on this. I hope you found this video helpful. Last thing you need to remember, the secret code word is going to be XOR. See you tomorrow.